Hey guys, welcome back. Today we're going to talk about continuity, but before we do that, since I don't want you to confuse continuity with limits, so before we get started, let's review a pretty straightforward problem on limits, one that you've seen before. Okay, so let's talk about first at x of 1. Does the limit exist at 1? In other words, what is the limit as x approaches 1 of f of x? Okay? Hopefully you're answering that question in your mind. Okay, think of your answer. Don't wait for me. You got it? Okay, hopefully you said that limit does not exist. Okay, remember, for the limit to exist, the left-hand limit has to equal the right-hand limit. In other words, the left-hand limit and the right-hand limit have to meet at that same spot. Now that spot where they meet can be a hole. It doesn't have to be a solid point. That's kind of the point of limits, okay? So remember, a limit is the height the function approaches from both sides, regardless of whether or not it actually reaches that height. But if they don't meet at the same spot, the limit definitely does not exist, okay? This would be my left-hand limit. This is my right-hand limit. But the overall limit would not exist. So, back to the question at hand, the limit as x approaches 1 does not exist. Now, if instead of saying the limit as x approaches 1, if I just added one itty-bitty little thing, and I asked instead the limit as x approaches 1 from the left, that answer would be the height as x approaches 1 from the left, which would be 0. So even though there's a hole there, the limit as x approaches 1 from the left is 0. Okay? The limit as x approaches 1 from the right would be this guy right here, 1. Now, if I ask you to justify whether or not the limit exists, since the left-hand limit and the right-hand limit aren't the same, you would say the limit as x approaches 1 does not exist because the limit as x approaches 1 from the left does not equal the limit as x approaches 1 from the right. And it is kind of tedious to write all of that, but it's an easy concept. Okay? So, how about at some of the other points, like 2? What would be the limit as x approaches 2? Okay, think about your answer. Okay, does the limit from the left equal the same as the limit from the right? Check. Then yes, the limit as x approaches 2 exists, and it would be the height that the graph approaches at 2, which is 1. This stray point up here, that has nothing to do with the limit, because the limit is the height the graph approaches, not necessarily the height the graph is actually at. This stray point up here is actually f of 2. F of 2 is 2, but that's not the value of my limit. Okay, so one more type of problem, one more type of spot. How about at 3? The limit as x approaches 3. Okay, the left-hand limit would be 2. The right-hand limit would be 2. Since those are the same, the limit as x approaches 3 is 2. So again, just to repeat and refresh and make sure you know what I'm saying here, the limit can be, the value of the limit can be an open circle and it can be a closed circle. But from the left and from the right, they have to reach the same spot. So here, since they don't reach the same spot, that's a case of the limit does not exist unless I specify left-hand limit and right-hand limit. Okay? So, again, the limit. The limit is the height the graph approaches from both sides, regardless of whether or not it actually reaches that height. So this can be an open circle or a closed circle, but the two sides do have to meet. Okay, so that's review. Let's move on to today's lesson. Today's lesson is about continuity. And continuity, the problems kind of look the same, so pay close attention. Continuity, a function is continuous. It's really common sense. A function is continuous if I can draw it without lifting my pencil. So, here you go. Here's a continuous function. Continuous, okay? Because I didn't have to lift my pencil. But if I went like this, now it is not continuous. I had to lift my pencil. There's a break in the graph. So if there's a hole or a break in the graph or a jump in the graph, then it's not continuous. Now, clearly that was pretty informal, so let me catch up with my PowerPoint. There's actually a formal justification for continuity that has a three-part definition. And sometimes you're required to justify continuity formally. And it's actually a pretty common question on the AP exam in the free response portion. So let me show you how you would justify continuity, okay? Let's use that same picture that we had before. Okay, I don't know what this little stray point is right here, so pretend it's not there. I don't know why that's there. Okay, let's first answer the question using common sense. Let's talk about the continuity at all the same places. Let's start at 1, okay? At 1, is the function continuous? Is it continuous at 1? Clearly not, no. But why is it not continuous? Well, the definition says that the limit at 1 has to equal the value of the function at 1. Okay? But the fact that the limit exists means that the left-hand limit has to equal the right-hand limit. So I usually put these two things together in a three-part definition. Here you go. In order for the limit to exist at 1, the limit from the left, as x approaches 1, would have to equal, hold on, I'm going to rewrite this. It's a little messy. Okay, so the limit as x approaches 1 from the left would have to equal the limit as x approaches 1 from the right, which clearly it's already broken, but that would also have to equal f of 1, okay? Now, let me try to show you what that means. In this picture, the limit doesn't exist, so it's obviously not continuous. But here's what would make it continuous, okay? If, let's say this is the left-hand limit, and let's say that hole right now, this is a different problem. Let's say that hole right there has coordinates 1, I'm making this up, 3, okay? So right now, the limit as x approaches 1 from the left would be 3, okay? Now let's add, using another color, the limit as x approaches 1 from the right. Let's say the limit as x approaches 1 from the right looks like that. It also has a height of 3. So the left-hand limit equals the right-hand limit. However, does it look continuous to you? No. That's because you need a solid point to be there. So the final piece of the three-part limit definition is you have to also have a solid piece here, a solid point. Okay? That would mean f of 1 is also 3. Okay? So these two pieces, if the left-hand limit equals the right-hand limit, that means they meet at that possible hole. This means there's also a solid point at that hole. Okay? There's a three-part definition. Left-hand limit equals right-hand limit, and those two things together could be summarized as just the limit exists, and it has to equal the value of the function. There has to be a solid point there. So now let's go back to this problem and talk about the other points, x of 2 and x of 3. Okay, first, common sense at 2. Is the function continuous at 2? No, because I have to pick up my pencil right there. Now, the formal justification when you say it's not continuous, you just have to say the piece that's broken. So, the left-hand limit does equal the right-hand limit, but it doesn't equal the value of the function. So here's how I write that. The limit as x approaches 2 from the left does equal the limit as x approaches 2 from the right, but it doesn't equal f of 2. Why? The left-hand limit is 1, the right-hand limit is 1, but f of 2 is 2. Okay? Now, that's how I always justify it. I always just use all three parts because it's easier for me to remember. But in actuality, if the limit exists, and only if the limit exists, then these two pieces could be written as one piece. The overall limit at 2 does not equal f of 2, if that doesn't confuse you. Okay, moving on to x equals 3. Okay, at 3, I think you can clearly see that at 3, it is continuous. Why? I don't have to pick up my pencil to get past 3. One solid piece. So at 3, it is continuous. So if the question was, is the function continuous at 3? I would say yes. Now, how do I justify that it's continuous at 3? Again, this weird point, I don't know what that is. To justify it, I would say at 3, the limit as x approaches 3 from the left equals the limit as x approaches 3 from the right and that also equals, and this is the piece everybody forgets, that also equals f of 3. Okay? And f of 3, that means you have a solid point there. What are all of those values? The limit from the left is 2, the limit from the right is 2, and the value of the function, they are all 2. Okay? So, one more time, let me summarize the definition of continuity for you. Okay, ignoring this problem, this specific problem, in general, the limit, the left-hand limit, the limit as x approaches some number that we'll call c, has to equal the limit as x approaches that same value from the right. But that's not enough. That simply ensures that the limit exists, okay? For it to be continuous, that hollow point has to be filled in with a solid point. Oops, sorry. Which means the third piece is f of c. Okay? If you change all of those c's to numbers instead of c's, it might be a little bit more clear. If this had coordinates 2, 5, then the limit as x approaches 2 from the left would be 5. The limit as x approaches 2 from the right would be 5, and f of 2 would also be 5, solid point. Okay? So, hopefully you understand the main idea for continuity. Now we're going to apply that to just a couple of problems. Okay. You don't really need to pay attention to what it's called. Jump discontinuity is the type of discontinuity where there's a break in the graph due to the left-hand limit not equaling the right-hand limit. But don't worry about that. More than likely, the question would be, ignore all of that and just say, is the function continuous at 0? Okay? Or even, is the function continuous? Well, this piece is a line, which is always continuous. This piece is a line, which is always continuous. So the only question here is, will the two pieces meet? Okay, let me show you graphically one more time what this would look like. This is a line, and at 0 there's an open circle. So maybe it goes like this, okay? Without me thinking about the math, the other piece, the bottom piece, this would be the right side. This is another line with a solid point at 0. At 0. So this piece would be, maybe it goes like this, and this is 0 and it's uphill. Or maybe it goes like this and uphill. So basically I have two lines, one on the left, one on the right. They meet maybe at 0. That's basically what we have in question. We need to know if the height of the left side meets the height of the right side. So how am I going to do that? Okay. To find the height of the left piece, plug in this 0. To find the height of the right piece, plug in this 0. And then we'll know whether or not they're meeting at the same spot. So let me erase all of this. Okay, plugging in the 0 to the left piece, I get 3. What that really means is the limit as x approaches 0 from the left is 3. Okay, now I'm going to plug in the 0 to the bottom piece, and when I plug in the 0 here, I get 1. Okay, well that means that the limit as x approaches 0 from the right is 1. So clearly it's not continuous. The limit doesn't even exist. So you can stop now. If these are not equal, it's not continuous. Okay? Now just to show you what that graph actually does look like, this is the left side. Sorry. The left side of the graph is I keep messing that up, so sorry. Okay, the left side of the graph is a line that stops at 0 but doesn't include 0. So that's this guy with an open circle, and it has a height of 3 because remember that limit on the left was 3. And the right side is also a line with a solid circle at 0. This is the right side. And the height at 0 is 1 because the limit on the right was 1. Okay, moving on. There's a stray piece on my PowerPoint here. Just ignore this. I'm sorry for my typos, but I'm not redoing this whole thing. It's okay. Go with it. All right, this is a very, very, very common question. Find the value of C that would make this continuous. Okay? Well, this is a line, which is continuous. This is a parabola, which is continuous. So the only thing that's in question is, will these two pieces meet at the same height? Okay? Will the line meet the same height as the parabola? Will it be like that, where in that case it wouldn't work? Nope, we want it to be so that the line and the parabola meet. And there has to be a solid point on one of them. That's what we want to happen. So in order for there to be a solid point for one of them, one of these has to have a solid line underneath that. We got that. Okay, so now we just need to figure out what value of C will make it so that these two pieces meet at the same height. So what do you think I could do to get that done? Okay, let me say it again, maybe put it another way. I need the height of this one to be the same as the height of this one. In other words, I need them to be equal. I need x minus 2 to equal x squared plus c. But at what point do I need them to be equal? I need them to be equal at that point where they meet, when x is 3. So basically, we just need to plug in the 3 to both pieces of this function. Okay, so I'm going to plug in that x is 3 here, and I'm going to plug it in here. And now it's really easy to solve that. That's the main idea. So, and you don't really have to show that step. So you get 1 equals 9 plus c, so c would have to be negative 8. Now what the heck does that mean? Okay, that's my answer. I'm done. C is negative 8. But what it means, if we go back to the original problem here, if c was negative 8, then this bottom piece of the function becomes x squared minus 8, which is a parabola, down 8. This is a line, and at 3, where they meet, they're supposed to be continuous. Well, let me show you what that graph actually looks like, and you'll see why I have this stray thing here in my PowerPoint. So now you see what that stray thing was in my PowerPoint, which I should really fix. Here's the actual graph, okay? The limit from the left is 1, and that one has the solid point. The limit from the right is 1 with an open circle, but since at least one of them has a solid point, it's continuous, okay? And that is because we ended up finding that c was negative 8, and that's what the graph looks like when you put it together. All right? So if I had to justify it, I would say the left-hand limit as x approaches 3 is 1. The right-hand limit as x approaches 3 is 1. And f of 3 is 1 because that's the one that has a solid point here. Okay, last one. Hopefully you're hanging in there. This one is usually kind of the trickier one, but you guys have already had some experience with these radical problems, so hopefully it won't be too bad for you. Okay, is the function continuous at negative 3? And you will also always have to justify this. So let me first talk about what is actually going on in this piecewise function. Okay, the top piece of the function, x cannot be negative 3 because if it was negative 3, it gives division of 0. Okay? Hopefully you remember that that means at negative 3, there's either a hole in the graph or a vertical asymptote. And we've already talked about when there's a radical, try rationalizing so that you can see that there actually is a hole in the graph, okay, because the x plus 3 ends up canceling. So this top piece, I'll give you a heads up, it is going to end up having a hole in the graph at negative 3. The rest of the graph isn't going to look like that, but whatever. There'll be a hole in the graph at negative 3. Okay? So then what is this? If this hole is at negative 3, and I don't know what the y coordinate is right now, this second piece, the bottom part here, is basically a straight point. And that straight point has the coordinates negative 3, 1/8. So what we have in question is that stray point? Is it a point that's down here, in which case the function is not continuous because there's still a hole in the graph? Or is this stray point right here where it fills in the hole in the graph? So that's what we need to figure out. we need to see if this stray point fills in the hole that this graph will have in it. Okay, so we're basically going to do what we did before and find the limit as x approaches -3, and that'll give me the height of this hole, and see if it's equal to f of -3. So let me erase this and do this last problem from scratch for you. Okay, so we're going to start with this part. What is the limit as x approaches -3? In other words, what is the height of the hole that this piece of the graph has in it? And we're going to do that like we did earlier in the week. I'm going to multiply by the conjugate and hopefully get this x plus 3 to cancel so that I can then plug in the value of this limit, plug in the -3. Okay, and technically I should have this limit out in front here. The limit, I ran out of space, but this limit should be out in front. The limit as x approaches -3 of this function I have in red. Okay, so I'm going to multiply by the conjugate. And you already know that that means just change the sign in the middle. Whatever I do on the top, I have to do the same thing on the bottom. Okay, now when you simplify that, remember it's not as bad as it looks. In the numerator, you're really just foiling something that looks like x plus 5 times x minus 5. Okay? If you foil that, it's just as easy. It's x squared minus 5x plus 5x and minus 25. And the whole point is these two middle guys go away. So remember, it ends up kind of sort of feeling like you square the first term and the last term, even though that's not really what you're doing. That's the point of multiplying by the conjugate. It feels like squaring the two terms with the two middle terms going away. It's not really squaring though, and you get a negative. I really need to get a better stylus for my iPad. I keep making things disappear that I don't mean to make disappear. I keep hitting buttons with my hand. Ay, ay, ay. So this is where we were at. We're multiplying by the conjugate because it kind of sort of feels like squaring. And remember, my goal, hopefully, is to make this x plus 3 go away because right now it's giving me division by 0 when you plug in that -3. So we're going to FOIL the numerator, okay? The square root of x plus 19 times another square root of x plus 19 would just be x plus 19. The outers are a positive for square root of bunch of junk, and the inners are a negative for square root of bunch of junk, so they cancel. And then the last term is -16. On the bottom, remember, we're not going to multiply that out because we're really hoping the x plus 3 will go away. We want it to cancel eventually. So I'm just going to rewrite that. And all this other junk too. Okay, now in the numerator you can see those parentheses really aren't necessary. So if I combine like terms, that's just going to give me an x plus 3. And hopefully bells and whistles are going off right now because now what I have is an x plus 3 on the top and magic, an x plus 3 on the bottom. We needed that to happen. And technically this limit was following all along the entire time. It really takes more time to write it than it does to think it. Okay, so now I still can't plug in that -3 for the limit yet, but as soon as I cancel these, now there's nothing on the top, which means there's a 1 there. And now that the x plus 3 is gone, now I can plug in my -3. I'm going to write it one more time, the limit as x approaches -3 of 1 over the square root of x plus 19 plus 4 is Now go ahead and plug in that negative 3 for x, because you can. Negative 3 plus 19, that would be 16. The square root of 16 would be 4, and 4 plus 4 is 8, so I get 1/8. And remember, once you plug in the negative 3, once you evaluate the limit, now this limit symbol goes away, and this is what I get. Now, what the heck was the point of all of this? Go back and read the question. Is this function that has two pieces, is this function continuous at negative 3? Well, this piece has a hole in the graph, and the coordinates of that hole are negative 3, 1/8. So as by itself right now, it wouldn't be continuous, but behind all my writing down here, in there we have a straight point. The straight point has coordinates negative 3, comma 1/8. So does that straight point fill in my hole? Yes, it does. Therefore, is the function continuous? Yes, it's continuous. And your formal justification would be the limit as x approaches negative 3 does equal f of negative 3. And you do have to show all that work to justify it. Okay, I hope you're doing well. Really hard to teach to nobody. Wish I could see your faces. Good luck with your homework. Bye.